Nowadays, having a few gigs of dedicated video RAM isn't exactly something to write home about. But going back to the likes of the NES, it's a much different story. With just 2 kilobytes of RAM, it had barely enough to be able to store its sprites in memory, and even then it had to make use of tiles and patterns to get by. So how were graphics even possible on the Atari 2600, a console with just 256 bytes of RAM, out of which just about 16 were even dedicated to graphics? As you might know, old TVs worked much differently from how they do today. Cathode ray tubes, or CRTs, got their images on the screen by firing electrons from a small cathode. The cathode moves along the screen in what is called a scan line. When it reaches the end of such a scan line, it has to turn off and move to the start of the next one where it can resume. Same for when it reaches the end of the screen. So how is this relevant? Well, as you can see, currently it's just drawing a plain white screen. To fix that, let's imagine we have a barrel in front of the cathode, where every chamber just contains a small pane of colored glass. If we write a program to rotate this barrel very quickly, we can use it to display the exact images we want. Although in reality, the color is of course decided by the intensity of the electrons, this on-the-fly manipulation of what colors are being drawn is exactly how Atari games do graphics. But enough weird visualizations about glass-pane gun barrels. Let's actually write a simple Atari program to ground these ideas. Atari code is of course written in pure assembly, so since we're gonna write 80s code, we might as well do it like in the 80s. Right, I fell asleep. Let's get back to work, I guess. Computer, give me something to work on.
I think as practice, you should try writing a program that just cycles through the Atari's color palette with a new color every scan line.
Oddly specific, but I mean, yeah, no, that sounds like a good idea. I guess I could put 0 into the X register and just do a loop that increments every scan line. But then, how do I actually draw that color?
To actually make our imaginary barrel rotate to the color in X, we store X at a special memory address 9 called column K.
Oh, okay. That doesn't seem quite right. Hey computer, what the hell is this?
Currently, it's not waiting for the scan line to finish before changing the color. For purposes like this, there are dedicated memory addresses that, when written to, no matter the value, perform a certain hardware function. For pausing any code execution until we are at the start of a scan line, we write a wsync, which is macro to address 2.
Then I guess if I fit it right there, that should do it. Let's give that a run. Oh, come on.
As you can see, now the color changes every scan line, but we still have it accounted for the time it takes for the beam to retract from the end of the last scan line all the way back to the start of the screen. To make sure we're
Wait, why didn't you just tell me all this at first?
I think this makes it easier for the viewers to follow along.
What are you talking about? What viewers? You're always saying this. Are you real? So, putting that confusing segment aside, with our updated code, which accounts for the beam retracting to the next scan line and back to the start of the screen, we now have a nice non-jittering rainbow background. And don't worry, we'll freshen up these graphics in just a bit. Now, this whole thing might seem silly, but this is exactly how backgrounds and other large graphics are drawn in Atari games. Before we get to player graphics though, there's something important we need to tackle. You might notice that in games like Pitfall, the background is much more than just a single color. There's things like leaves and water. To draw complex stuff like this, we have to accurately time our writes to column K to happen at just the right pixels. This is where it becomes clear exactly how much the Atari graphics go hand in hand with its processor. Every instruction that can happen in a processor takes a certain amount of CPU cycles. This can depend not only on the instruction, but also the addressing mode, the input parameters, and the CPU state. The time it takes to perform one CPU cycle is equivalent to the time it takes for the cathode to draw 3 pixels. So if you want to switch the background color out for a green leaf color to draw trees, we have to calculate exactly where in the code to put these color swaps. This can of course become incredibly difficult and tedious due to how many different factors can affect each instruction's cycle count, and well, we already saw what can happen when writes get offsetted incorrectly, though this cycle stuff isn't just relevant to drawing the background either, as you'll come to see. Now, with this knowledge, let's modify our code a bit so it looks more like an actual game. You can see a lot of no operation instructions, which just make the CPU halt for a few cycles. Now, we have a nice beautiful background, but it's rather empty. To fill in this empty screen, we have 5 different objects, all implemented into the hardware in different ways. There's 2 players, 2 missiles, and of course to top it off, a ball. You might notice from this rigid set of objects that this console was originally designed for simple Pong-style games, or as the author of a popular Atari emulator written in assembly put it,
hardware sprites are notably called players, missiles, and ball. Being manufactured in the Cold War era, the implied purpose of this gaming console is playing joyful war games. War is not a game. War is no fun. War is murder.
What assembly programming does to a guy, huh? Thankfully, although very similar to drawing the background, player graphics are not quite as tedious, since we can just store them in memory, right? Well, partially. There are 2 bytes in memory dedicated to the player graphics, 1 byte for each player respectively. You might wonder how one stores an entire player graphic in just 1 byte. Well, you can't. Each bit at these locations represents just 1 pixel that will be drawn on the current scan line. This means you have to update the memory as the players are being drawn. There's also 3 color bytes that control the color of multiple objects at once. Here's my attempt at implementing player graphics. You might wonder why suddenly the trees are messed up on certain scan lines. This is because to decide what part of the player we should be drawing, we have to perform comparisons and branching instructions, which all take different amounts of cycles, resulting in an offset on those lines. The last thing we have to take care of is creating some terrain for our character to platform over. I didn't really stop to consider what kind of game this was actually going to be. Now, this might come as a surprise, but most terrain is not actually drawn with Column K. The reason for this is that there's a few special bytes dedicated to drawing the playfield for which the collisions with other objects are automatically checked in hardware. The playfield actually works in the exact same way as the player graphics, except its graphic is 2.5 bytes, and it's drawn over the entire screen. Since the playfield is so similar to player graphics, we also code it in a similar way. We just check what scanline we're on and update the data accordingly. And there we go. Now that our motionless hero is faced with some obstacles, our game is ready to ship. Now, this was of course far from everything there is to Atari graphics, but that was about all I had to say on the topic. I hope I managed to give you an appreciation for the complexities of programming for older systems. It's easy in modern day development to treat computers as limitless machines that can do anything in the blink of an eye. But I think it's important to once in a while take a step back and realize we really are standing on the shoulders of giants.